Okay guys, welcome back to the second part of 2D projectiles. We're going to take on the diagonal case in this lesson. And I'm going to start with an activity that's not in your workbook. You're welcome to draw this on a separate piece of paper and give it a try, or just think about it. Can you answer what the direction the velocity vectors will be and the acceleration vectors will be in all these different locations? Give it a try. Pause. Okay, so being true to the color of the velocity at the beginning here, let's draw the velocity vectors as you go up. Now, I hope you understand that as the object goes up into the air, up towards maximum height, it's going to slow down, slow down, slow down. So the velocity vector will get smaller in magnitude. And notice it's a curved pathway, a parabolic pathway. But we need to draw a straight arrow on a curved pathway. And hopefully you were thinking tangents. So, in the first row position, it'll be on the tangent, but it'll be a smaller velocity. And at the top, the tangent would be perfectly horizontal and on the tangent and smaller. And that would actually be its smallest speed up at the maximum height. And then, as it's coming back down, it starts to speed up, stays on the tangent, and stays on the tangent, speeding up as you're going down. So the velocities on the tangent. Good. Now what about the acceleration vectors? Well, this one's kind of a trick question because this is a projectile. If you remember, a projectile, the acceleration will always be equal to 9.81 meters per second squared downward at every given location. So if you really wanted to show that, you would have the downward acceleration, and it's the same all the way through the entire motion. This is the acceleration vector, if you wanted to show it. But it's a constant acceleration all the way through. Good to know. It doesn't change while it's flying through the air as long as there's no air resistance. Good. Okay, let me eliminate those parts. I just want to show you one more thing. Let's talk a bit about the components. This will inspire us for the next part of our lesson. If we actually draw the component, anytime you see a diagonal vector, you should be thinking, let's draw some components here. Well, it turns out in the first one, we have this horizontal component, like that, and then we have a vertical component. Let me do them as two different colors, distinct colors. So those are the two components of the initial velocity. Now, if you remember, since the acceleration, and I suppose I'll just put one here, since the acceleration is always the acceleration due to gravity, there's only a vertical acceleration. There is no horizontal acceleration. So therefore, that horizontal component will stay the same all the way through. So that will stay the same. And then it'll stay the same. And it'll stay the same. And it'll stay the same. So that horizontal component, give or take, a real rough diagram. But that blue vector stays the same all the way through, constant horizontal velocity. But vertically, we know that as it's moving upward, it's going to slow down. So it's going to have a smaller vertical component here. And when it gets to the very top, there is no y component at the very top. It's neither moving up nor down. If it was still moving upward, it would keep going up. It wouldn't be at maximum height. And then when it's coming back down, it'll start to speed up. It'll speed up, and it will speed up all the way along. Good? And you'll see that that's very consistent with horizontal projectiles. Constant horizontal velocity, and the vertical is accelerating, which means we can use the same method. But the key, as we're going to find out, the key is because you have a diagonal initial velocity, the first thing you have to do is draw its components. So let's give it a try. So now we have a classic golf ball question. Let's draw this first. I'm going to do a nice big diagram here so I can make full use of it. But here's the golf ball at the beginning, launched at a speed of 78 meters per second at an angle of 23 degrees above the horizontal. And we know this thing is going to be going up and then coming back down on the other side, making that beautiful parabolic pathway. And our job, similar to the question we did last day, is we just need to figure out the horizontal distance. How far is that? Okay. Now, do you notice how the initial velocity is diagonal? Anytime you see a diagonal vector, what's your first instinct? Answer, to find its components. So let's find the components of this vector. So this is what you do for diagonal vectors. Here's the horizontal component. We'll call that v initial x. And then we have the vertical component, v initial y. So why don't we find those first, and then we'll go from there. We'll do the quick technique we talked about before. So v initial x becomes equal to the hypotenuse. And because v initial x is adjacent, that's going to be cosine of 23 degrees. And if we use just kind of a standard reference system, then this would come out to be a positive value. And I'll just quickly do the other one as well. So v initial y is the hypotenuse sine. And it will also be positive. All right, so again, make sure you're in degree mode. So the horizontal is about 71.8 meters per second. And the vertical is 30.48. And there we go. And if you want to, you can put those on the diagram. So v initial x, 71.8. And then v initial y, 30.48. Done. Okay, that's step one. Now, in order to solve this question, we're going to do a very similar strategy to what we did in the previous one. We're going to divide this up into horizontal and vertical. So let's start with horizontal, since that's kind of what we're looking for here. So remember, horizontally, we know the acceleration, and if you want to draw the acceleration on here somewhere, you're absolutely welcome to. We know the acceleration is going to be equal to gravity the entire time. It's on the vertical, on the y-axis only. So horizontally, there's no acceleration. Which means horizontally, which is in the x, we know that the acceleration in the x is 0. So this is going to be uniform motion. And again, because the acceleration in the x is equal to 0, what equation are we allowed to use? And that's going to be v is equal to delta d over t. Make sure you put an x here, x here. And if we look at vx, we already know what that is. And if we talk about vx, I'll just show another few locations, just like we did earlier. I'll put the object there, then at maximum height, then here, then just before it lands on the other side. And if we show the components here, horizontally, that horizontal component will stay the same all the way through the entire motion. So that will always be 71.8 meters per second all the way through. Constant horizontal. And although it's a little bit messy in here, can you draw the overall displacement vector? And again, I'm just going to choose a color here that doesn't ruin this diagram. But displacement goes from start to finish. So that would take you all the way across from start to finish. This is the delta D, which happens to be the delta dx. And that happens to be D. So delta D is delta dx. That's kind of what we're looking for here. All right, so let's do that. Let's get the delta dx by itself. So the big D will simply be equal to Vx, and we saw that Vx is 71.8. That stays constant all the way through. And we just have to multiply that by the time of the journey, and then we'll figure out the horizontal distance. But how do we find the time? Well, much like we did in the previous question, we have to do vertical. So bear with me. I'm going to just copy this and bring it to the next part. Let's copy that. I think I might need, oh no, I'm good. Paste that, shrink it a little bit. Okay. So there's our diagram again. Let's go vertical now. So vertical, and we know that for vertical, this is definitely going to be accelerated motion. It is definitely accelerating. And again, if there's acceleration, then we should be thinking V initial, V final, A, delta D, and T. And I'll just put some Y's here. Y, 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 Y. And let's talk a bit about the vertical component. I'll just choose a different color for this. Running out of colors. But you'll see how the V initial Y is that. Okay, that's what the V initial Y was at the beginning. But as it moves upward, it gets smaller. And then at the top, there's no V initial Y, or no Vy at all when it gets to the very top. Then it comes back down, and it starts to speed up. And it starts to speed up. And notice it comes right back down to the very same height. And this part at the bottom here, remember this V initial Y is 30.48. And there's our V final Y right at the end. Okay, now for making our list, V initial Y we know as 30.48 meters per second. Do we know V final Y? And it turns out we actually do, because it came to the very same height as it started. And due to symmetry, this will also be 30.48 going downward. Remember, that's only if it's at the exact same height. So that means on our list, this will be equal to negative 30.48 meters per second. We know the acceleration is going at 9.81 meters per second squared downwards, so that'll be negative. Do you know what delta dy is? Turns out we do. There is no delta dy. It is entirely horizontal. So the delta dy is actually 0. But it turns out that even though we know this, we don't need it to solve this question. So I'm just going to leave that. And remember, we need to figure out this time so we can bring that back to the horizontal analysis. So our equation for this one will be acceleration is equal to change in velocity over time, or simply V final minus V initial over time, cross multiply, AT, V final minus V initial, and then get T by itself. Okay, so that's going to be negative 30.48 minus 30.48 all over negative 9.81. And that's about 6.21 seconds. So now we can take that time and bring it back up to here. So that's 6.21. Just multiply that by 71.8. And we get about 446 meters. All right. And that's how we take on a two-dimensional question. Good news for you. It is a similar method to what we did with horizontal, but what you need to remember is when you start this question off for diagonal, anytime you see a diagonal vector, like we did here on the left, we saw this was a diagonal initial velocity. First step is to find the components, x and y. Once you've done that, then it's a similar method. Now we do horizontal, which is a constant velocity. V is d over t. And then we do vertical with v initial, v final, a dt. And this will be the hardest part of the question, the vertical. And to make sure you get the vertical down pat, I do recommend you draw a very clear diagram like what you're seeing here. Show your work on the diagram to understand the question, and that will help you. Okay? All right. We're good. We've actually finished the unit. I wish you all the best on the unit exam. I'll see you in the next unit.